Welcome back, everybody. In this tutorial, you are going to code a queue learning network to beat the mountain car environment using only Numpy. You don't need any prior experience. You don't even need to know anything about the OpenAI gym or reinforcement learning. You just need to follow along. Let's get started. So the first place I like to start when tackling a new environment is to take a look at the documentation. The reason we want to do this is because we need to know the limits on the action and position spaces. And of course, here on OpenAI, the OpenAI Gym's website, you don't see any real information on the limits. But if you take a look at the source code on GitHub, you can see that the position has a min and a max, and these speeds also have a maximum. And of course, this maximum is going to be plus or minus. As you can see here, it has plus and minus max speed in the low and high NumPy arrays. So we already, off the bat, just by looking at the source code, know our environment's parameters. So first thing we want to do then is head back to our editor and start coding up the problem. So let's start with our imports. And of course we'll need NumPy, we'll need gym, and matplotlib. And we'll want that to plot the score the agent receives over the course of the episode as a function of time so that we can verify its learning. The first problem we have to solve is the fact that we're dealing with a continuous state space. The position can be anywhere from minus 1.2 all the way up to 0.6, and the velocity can be minus 0.07 all the way up to positive 0.07. You can't have a dictionary that maps continuous values as keys, so we have to turn these continuous values into discrete ones, and we're going to use NumPy to do that. In particular, two separate functions. What is called linspace creates a linear space where you specify the two endpoints and the number of buckets you want, and it'll create a set of buckets within that interval so that you can take an observation and place it in one of those buckets. That'll turn a continuous number into a discrete one. The inverse function of that is digitize, and that actually does that operation where it takes the buckets and it takes the observation and tells you which bucket that observation falls into. So the first thing we want to do then is create our position space linspace, and that goes from minus 1.2 to 0.6. We're going to give that, let's say, 20 buckets. You don't want to have a really large number of buckets because that's not a whole lot better than having a continuous number, but you don't want so few that you don't capture any of the granularity of the environment, right? You want different positions to have different values, right? So you don't want too few buckets, but you also don't want too many. Likewise for the velocity space. Help if I could type. We'll give that 20 buckets as well. Next, we have to do the inverse operation. So we'll define a function that takes an observation and returns a state. So the observation is a tuple whose elements are position and velocity. And then we want to get the bins using the digitize function, and it takes our position as input and the position space. Likewise for the velocity. And we want to return a tuple of position and velocity bin. So we send in an observation, which is a tuple of two numbers that are continuous, and we end up with two integers on the output. So now that we have defined our function to take a continuous observation and turn it into a set of discrete ones, let's go ahead and test that out. So we'll go ahead and make our environment. We'll play a single game. We don't need too many to see this. And we'll just iterate over those games. We'll set our done flag to false for each episode. And let's get our initial state. That's env.reset. And let's say state equals get state for observation. And let's go ahead and print out the observation and the state so that we can see how that works at the beginning. And then we will go ahead and play an episode. And not NumPy, sorry, it is the env.action_.sample function. If you aren't aware, what this will do is it will query the environment for its action space and take a random sample of it. That way we don't have to do a NumPy random choice. It just makes sure we get something that's an action that's actually in the action space. So then you want to take that action and you get a new observation. We'll say new state equals get state observation. And we'll have an input statement so it doesn't fly by too quickly. So let's run to the terminal and watch the output of this to see what we get. Okay, so let's go ahead and run the mountain car problem. Matplotlib. Alright, there we go. Okay, so our observation comes out as the initial state is minus 0.40 and 0 velocity. So that puts it in bucket 9 and bucket 10 for velocity, respectively. So minus 0.4 and minus 0.0018. Okay, that makes sense. So let's keep running that, and you can see that as the velocity changes, it moves from the 10th bucket into the 9th, right? So pressing it more times, you can see that it eventually transitions into the state 8, 9. And so we can see that our getState function is working precisely as we intend. We put in a continuous observation and get out a discrete one, and you can see that there are some boundaries to this. So everything is working as it should. Let's go ahead and exit that, clear, and we'll head back to the editor to finish the actual algorithm. So before we start coding, it behooves us to take a look at the algorithm we want to implement. So what you're looking at right here is the textbook Reinforcement Learning by Sutton and Barto. These guys have been in the reinforcement learning game for decades, and they've written the definitive textbook on the fundamentals of the topic. So this is the algorithm we want to implement. The first step is to initialize the Q estimate for all state and action pairs in our state and action space arbitrarily, and set the estimate for the terminal state for all actions equal to 0. So if you're not familiar with Q, Q is the Q of Q learning. What it stands for is the agent's estimate of the future rewards it expects to receive given it is in some state S and takes action A. So it's just an estimate of how much of a reward the agent is going to get for the state and action pair. And of course the estimate for the terminal state has to be 0, because once you're in the terminal state, the game is over, right? No future rewards follow. So we want to repeat for each episode, initialize our state, and then iterate over the episode itself. Choose an action from the state using the policy derived from Q, e.g. epsilon greedy. Epsilon greedy is a type of action selection where the agent will draw a random number, and if that random number is within some range, it'll take a random action. Otherwise, it will take a greedy action, meaning the action that lets it transition to the state with the highest future reward. Take that action, observe the reward, and get your new state, and then update your Q estimate with the following equation. This is how the agent learns to effectively dominate the environment, by updating this QSA table by sampling the environment using epsilon greedy. And the important things to note here are we have this quantity alpha, that is a learning rate like you have in deep learning. R is your reward. Gamma is a discount factor that tells us how much the agent values future rewards. A value of 0, if you plug that in, you see that the update equation is just alpha times R. That means that it is only counting the immediate reward. If you set gamma equal to 1, then you can see that it takes into account the reward, it gives maximum weight to that quantity Q, S prime, and A. So it is a factor that tells us how much it values future rewards. Typically we'll set it to something close to 1, like 0.99995, something like that. Other thing to note is that we have this function here, max over action of Q, S prime, and A. So we need a function that calculates the maximum action given the agent is in some state S prime. We can write that in a second. So you'll need all these parameters to update Q, set your old state to the new state, and iterate until the state is terminal. So this seems pretty reasonable. If it's mysterious to you, don't worry. We're going to go ahead and code this up presently, and you'll see it's actually pretty straightforward. Let's head to our code editor and get to work on that. Okay, so the first thing I want to do is to code up that max action function, and we need to do this because the Numpy argmax function won't quite do precisely what we want, because we're going to be dealing with a dictionary. So let's go ahead and do that first. And that max action function takes in Q, the current state, and we're going to want to know the action space. For this environment, it is a set of integers 0, 1, and 2. So we have to go from a dictionary representation to a NumPy array representation, so let's do that. So all we're doing here is, yes. So all we're doing here is constructing a NumPy array out of the values for Q of S and A for all the actions in our action space. Then we can say that the action we want to take is NumPy argmax of that array values. And we can just return that. So that is how we're going to find the max action, and we use this both for epsilon greedy action selection and for updating our estimate for the Q table. Let's come down to our main function and define our hyperparameters. We'll start with learning rate alpha 0.1. Use a gamma of 0.99. We also need an epsilon for epsilon greedy action selection, and we want that to start out at 1.0 in the beginning, so the agent takes totally random exploratory actions starting out. We're going to gradually decrease this over time to a finite value, so the agent eventually settles on an almost entirely greedy strategy, but continues to execute some number of exploratory actions to make sure its estimates for Q are accurate. Speaking of which, let's go ahead and construct our state space. So we have 20 buckets, right? So the positions are a range of, 21, because we have 0 to 20. And the velocity space has also a range of 21, because that's 20 buckets. So you want to append that pair of position and velocity. So this is how we're going to construct the keys for our dictionary, and that's why it has to be a tuple, because dictionary keys in Python have to be immutable objects. Strings, lists, things like that are mutable and cannot be used as dictionary keys. So next let's define Q. And let's say for action in, let's say 0, 1, or 2, let's say Q state action equals 0. And so this is an arbitrary estimate, certainly, and it will automatically cover the case of setting the terminal state to 0. Next up, we want to play a number of games. So let's come back up and say we'll play, instead of one game, let's play 50,000 and get rid of the print statement. We definitely need these. Let us say that the score for the episode, we'll define it up here, is 0. If I modulus 1000 equals 0 and I greater than 0, let's say print episode I score and epsilon. We'll go ahead and print the epsilon every 1,000 episodes so you can see how the agent is learning over time. Perfect. So then what we want to do is go ahead and say score equals 0 again at the top of every episode. Of course, we have to do it once at the top so that you can actually print something here, but you don't want to set this at the top, otherwise you'll always print 0, right? So then we come down to our main function. We can say score plus equals reward. We can take care of that easily. We want to get rid of this action space sample because we don't actually want to do that. What we want to do is say we need a random number, and we want to take a random action if that random number is less than epsilon. Otherwise, we want to take a maximal action. So action equals np random choice 0, 1, or 2 if np.random.random less than epsilon, else max action q state, and we pass in action, and it has a default value for action space. Okay, so that will take an epsilon greedy action. We'll go ahead and execute that action. We get the new state, keep track of our score. So the next thing we need to do is to calculate our update equation for Q. First step in doing that is calculating the maximal action for our new state. And then we can plug that into the update equation for Q. Q state action equals Q state action plus alpha times a quantity R plus gamma times Q state underscore action underscore. Let's go ahead and put that on a new line. And then minus Q state action. That's our update equation. Pretty straightforward. So now that we have our update equation taken care of, we need to set our current state, the old state, equal to the new state. Other administrative stuff to take care of, we didn't do it up here, but let's go ahead and keep track of our total rewards over time. And that'll just be a numpy array of zeros of size n games. So 50,000 games. And then you can say total rewards I equals score. That goes outside of the episode at the end. And the next decision we have to make is how are we going to decrease epsilon over time. So I'm going to do it linearly. Epsilon equals epsilon minus 2 over number of games if epsilon is greater than 0.01, otherwise set it equal to 0.01. So this will reduce it to almost entirely greedy action selection strategy by halfway through the number of games. Finally, we want to print out, we want to plot the performance of our agent over time. So let's do that by plotting the mean rewards over time. That'll kind of average out the noise that's inherent in the Q-learning algorithm, so we'll see somewhat of a more smooth curve. So we'll say mean rewards equals numpy zeros n games, and for t in range n games, mean rewards t equals numpy mean total rewards max of 0 or t minus 50 up to t plus 1. This gives us a running average of the previous 50 games. And let's save it to a file. And that is that. So now we can head to the terminal and see if I made any typos or mistakes. Let's do that. All right, let's give it a shot. Name R is not defined. Of course, it is reward. I'll just type that, reward. There we go. So it is running, and it'll hit the first 1,000 games, and then epsilon not defined. That's because I call it eps. There we go. There we go. Of course. Of course. So what I did wrong is I put comma epsilon instead of percent. There we go. There it goes. Okay. So after the first 1,000 games, it's already down to an epsilon of 0.96. And it gets a score of minus 200. I did forget one thing. So it is hitting the minus 200 wall every single time. Now, from personal experience, I know that 200 moves is not enough to actually solve the mountain car environment. And unfortunately, this is the default that OpenAI Gym sets for us. So do we just give up here and say it's hopeless? No, we can actually tweak the max steps for the environment to something that allows the agent to actually learn to play the game. It boils down to the fact that 200 moves isn't enough to take random actions and actually solve the environment. So let's go ahead and head back to the code editor and do that. So here we are, and what we want to do is change the max steps parameter. I believe that's what it's called. Say env dot underscore max episode steps equals, let's say 1,000. So 1,000 is enough to get us what we need. 50,000 games may not be enough. I'll let it run, and if it isn't quite enough, then I will go back, rerun it, and see how it does. So let's go ahead and head back to the terminal and start running and see how it does. Okay, let's try running it again. So there it goes. It took a little bit longer because it's playing, 5 times as many steps per episode. So you can see it's getting the maximum number of steps that it can, so it's not actually solving the environment. You wouldn't expect it to with a 96% chance of taking a random action. So I'm going to let that run all the way up to 50,000 games and see how it does. I'll come back and we'll see how it does at that point. And we're back. So this finished running in, 10, 15, 20 minutes, something like that. I walked away. You can see that the score does indeed increase over time as the agent's epsilon goes down and down and down. It eventually settles on something like around, 140 moves to solve the environment, 150, 160. And if you take a look at the plot, you can see clear evidence of learning where it starts out with the first few thousand games kind of struggling to beat the environment and eventually increasing significantly over time to approach a limit of around minus 150 or so points to solve the environment with some oscillations in there. I suspect if we allow this to play many, many more games, something like 200,000 or so, that we would get a much more stable performance at the end. And the reason is that the state action space is relatively large, so the agent has to visit each chunk of that many, many times to get a nice stable estimate for its queue function. So that is clear evidence of learning, and all of this with only around 50 or 60 lines of code. Really, the algorithm itself was only a few lines, relatively straightforward and quite powerful for even modestly complex environments. So that is quite useful for future algorithms. Feel free to use this code. You can find it on my GitHub, and this can be applied to many other different environments as well. So I hope this has been helpful. If it has, smash the like button, share the content, and I'll see you all in the next video.